Hey everyone, welcome back to the channel. If you enjoy journeys into space, strange physics, and ideas like gravastars and black holes, please remember to like the video, subscribe, and share it with someone who loves science as much as you do. It really helps the channel grow, and I appreciate your support a lot. Before we start, I'm curious, what time are you watching this, and where in the world are you right now? Let me know in the comments below. Now, let's dive into the most terrifying alternative to black holes. Massive stars live their lives in a delicate balance between gravity pulling inward and radiation pushing outward. For millions of years, this balance holds as nuclear fusion in the core converts light elements into heavier ones and releases energy that supports the star against its own weight. Eventually, the core fills with heavy nuclei that no longer provide useful fuel, and the balance begins to fail. Gravity slowly gains the upper hand until in its final moments, the internal structure of the star can no longer adjust smoothly. The support vanishes almost at once, and the core starts to collapse in free fall, shrinking from a sphere many times larger than a planet to an object smaller than a city in a fraction of a second. Under these conditions, matter is compressed to densities far beyond those found in ordinary atoms or even in the nuclei of atoms. Protons and electrons merge into neutrons. Neutrinos stream outward, and a powerful shock forms as the outer layers crash into the rebounding core. The star dies in a supernova, an explosion so luminous that a single object outshines an entire galaxy, for a short time releasing more energy in seconds than the sun emits in its whole lifetime. Modern telescopes observe these events across the universe, detecting their light in visible wavelengths, in high-energy gamma rays, and in X-rays, and tracing their aftermath as expanding shells of gas and dust. Computer simulations on powerful supercomputers reproduce many features of these explosions, from the rapid collapse to the violent rebirth, and they show that the fate of the core depends strongly on how much mass the original star contains. For some initial masses, the collapse stops with a stable neutron star and object a few tens of kilometers across with a mass roughly similar to that of the Sun. For higher masses, the calculations usually show a different outcome, in which gravity overwhelms all known forms of pressure and forces matter to continue collapsing into a region where familiar physics breaks down. This result matches the mathematical description of a black hole, a region from which nothing can escape once it passes a certain boundary. In general relativity, the theory of gravity that describes how mass and energy curve space-time black holes appear as simple solutions to the equations. Their external properties are defined by only a few numbers, such as mass and spin, and many different collapse histories settle into the same final state. Observational astronomy gives strong support to this picture. Stars near the center of the Milky Way orbit an invisible object with a mass equivalent to several million suns. Their motions tracked over decades with precision instruments by observatories such as those run by the European Southern Observatory point to a very compact mass concentrated in a region smaller than the orbit of Mercury. In distant galaxies, bright X-ray sources vary on timescales of seconds and minutes, indicating emitting regions only a few hundred kilometers across. Yet the inferred masses are many times that of the Sun. Radio telescopes working together across the Earth form instruments with the resolution needed to map the shadow of the central object in some galaxies, revealing a dark region surrounded by a ring of emission consistent with expectations for gas, flowing near a black hole. These results, combined with detections of gravitational waves from merging compact objects by facilities on Earth, have made black holes a central element of modern astrophysics. They offer an elegant way to explain extreme gravitational fields and compact masses, and their properties fit well within the framework of general relativity, tested in many other contexts. Yet the idea that matter collapses into a point of zero size and infinite density raises deep questions. At the center of a classical black hole lies a singularity, a region where the equations predict that curvature becomes infinite, and where space and time lose their usual meaning. The event horizon, the boundary around a black hole beyond which no signal can return, hides this singularity from outside observers, but it does not remove the conceptual issue. When quantum effects are considered, the situation becomes more complex. Theoretical work suggests that black holes slowly emit radiation and can, in principle, evaporate over very long timescales. If this happens, information about the matter that formed the black hole seems to disappear in conflict with the usual rules of quantum mechanics that preserve information. This tension between the predictions of general relativity and the principles of quantum theory is often called the black hole information problem. For decades, it has motivated the search for a more complete description of gravity at very high densities. Within this effort, some researchers have explored alternative endpoints for gravitational collapse solutions, in which the core does not continue all the way to a singularity. One candidate is the Gravastars, short for gravitational vacuum star and object, where the collapsing matter triggers a transition of the vacuum itself inside the star. In this picture, the central region does not contain a singular point, but instead a sphere filled with a special form of vacuum energy surrounded by a very thin shell of exotic matter. From the outside, such an object would mimic almost all observable features of a black hole. From the inside, it would be something entirely different. The idea emerges from attempts to combine quantum field theory, which describes particles and forces in terms of fluctuating fields, with the curved spacetime of general relativity. In such models, vacuum energy can respond to extreme compression by changing its effective properties so that the interior of the collapsing star is replaced by a region dominated by this energy, rather than by ordinary matter. The outer layers, forced to adjust to this new interior, can freeze into a very compact, cold, and rigid shell. The complete object still satisfies the equations of gravity, and for an observer far away, its gravitational field is almost indistinguishable from that of a black hole of the same mass. The difference lies only in the deep interior, where the familiar singularity and event horizon are replaced by a finite radius surface and a core that behaves more like a patch of accelerated expansion than like a point mass. When the core of a massive star collapses, the process is usually described as a smooth march toward either a neutron star or a black hole. In reality, the interior evolution passes through conditions that are difficult to explore in any laboratory, and that push known physics to its limits. Densities rise far beyond those of atomic nuclei, temperatures soar, and the space-time curvature becomes extreme. Under these circumstances, the equations of general relativity coupled with quantum field theory admit more than one possible outcome. A Gravastars scenario begins not with a sudden appearance of something exotic, but with the familiar collapse of matter under gravity that then takes an unusual turn. As the core contracts, the pressure from ordinary nuclear interactions strives to halt the infall. In some ranges of mass, this partially succeeds and leads to a neutron star. In higher mass cores, the pressure is not enough, and classical calculations show the collapse continuing inward beyond any stable configuration. The idea behind a gravastar is that before a true singularity forms, the nature of the vacuum inside the star changes. Instead of particles and fields sitting on top of an essentially passive emptiness, the vacuum itself becomes an active component. The energy associated with the vacuum, usually negligible on stellar scales, can be promoted to a dominant role when matter is squeezed past a certain threshold density. In theoretical models, this transition can be described as a change from a normal interior to one filled with a form of vacuum energy similar to the one that drives the accelerated expansion of the universe on the largest scales. To picture the sequence, it is helpful to follow a small volume element at the center of the collapsing core. Initially, it is filled with extremely dense nuclear matter, a mixture of neutrons, protons, and other particles packed together. As gravity tightens its grip, this mixture becomes unstable. According to some proposed equations of state which relate pressure to density and temperature, there is a point where no arrangement of known particles can provide the pressure needed to resist further collapse. At this stage, quantum effects associated with the vacuum come into play. The vacuum energy inside the shrinking region can increase dramatically in response to the extreme curvature and compression. The matter content effectively dissolves into a high-energy state of the underlying fields, leaving behind a region dominated by this vacuum energy rather than by conventional particles. In the simplest gravastar models, the interior is treated as a sphere filled with constant vacuum energy density. This region behaves in a way that resembles a small patch of cosmological expansion, where negative pressure acts as a repulsive gravitational source. In the middle of a collapsing star, such a repulsive interior resists further contraction and pushes outward against the surrounding matter. This outward push does not simply reverse the collapse and blow the star apart. The outer layers of the core and the infalling envelope of the star are still plunging inward at high speed. They carry enormous kinetic energy and momentum. When the expanding tendency of the vacuum-dominated interior meets the infalling matter, the interaction can be violent. The matter is compressed in a narrow region between the inner vacuum core and the outer collapsing material. In that region, densities and stresses may exceed those inside any neutron star and approach theoretical limits beyond which known forms of matter cannot exist. Some gravastar constructions assume that in this narrow band, matter is transformed into an exotic state that has properties unlike any familiar substance. It may be extremely stiff, meaning that it resists compression with enormous force, and at the same time almost perfectly cold when seen from outside. The result is a shell with a thickness that can be many orders of magnitude smaller than an atomic nucleus, yet strong enough to confine the vacuum energy inside. In traditional black hole formation, there is no such stable shell. The collapse passes through the horizon and continues toward a singularity, while from the outside the surface appears to freeze near the event horizon due to gravitational time dilation. In the gravastar picture, the presence of a vacuum-dominated core and a stiff shell changes the story. Instead of matter crossing an event horizon, the collapse is halted just outside the radius that would correspond to a horizon for a black hole of the same mass. The shell forms at this radius and supports itself through the balance between the outward push of the interior vacuum energy and the inward pull of gravity from the total mass. The metric, the mathematical object that encodes the geometry of space-time transitions from an interior form appropriate to a vacuum energy-dominated region to an exterior form that almost exactly matches that of a black hole. The difference lies in the fine details near the would-be horizon where the shell resides. Building such a structure in nature requires extreme conditions, but those conditions are naturally present in the death of very massive stars and in the mergers of compact objects. The central question is whether the physics of matter and vacuum at those densities truly allows the required transitions. No current experiment can reproduce the relevant combinations of gravity, density, and temperature. Instead, physicists simulate these environments using numerical relativity and high-energy theory on supercomputers. They explore how different assumptions about the behavior of matter at ultra-high density affect the outcome of collapse. In some ranges of model parameters, the equations evolve towards solutions that resemble gravastars, a finite radius, a strong gravitational field outside, and an interior without a singularity. In other ranges, the familiar black hole solution remains the only stable endpoint. The uncertainty reflects both the complexity of the equations and the incompleteness of our knowledge of matter under such extreme conditions. Yet, the mere existence of such alternative solutions within the same broad theoretical framework suggests that gravitational collapse might not always have a single inevitable ending. The grinding of a star into what looks like nothing could in some cases be the route to a gravastar rather than to a classical black hole. In the gravastar picture, the most striking feature is not the interior, which hides behind theoretical descriptions of vacuum energy, but the boundary that separates that interior from the outside universe. This boundary is the shell, a layer of matter so thin and so extreme that it has no straightforward analog in ordinary astrophysics. In simple models, the shell forms at a radius only slightly larger than the radius where an event horizon would arise for a black hole of the same mass. The gravitational field at this location is intense, strong enough to bend light into tight orbits and to slow the passage of time for any process near the surface when compared with distant observers. Within this setting, matter compressed between the outward push of the interior vacuum and the inward weight of the overlying star can settle into an unusual state. The equations that describe this state are written in the language of general relativity and energy momentum tensors, but their physical content can be summarized more simply. The shell must be stiff enough to resist further compression from the enormous gravitational pull of the total mass, and yet light enough and thin enough that the geometry just outside it closely matches that of a black hole. To meet these conditions, the shell material is assigned an exotic equation of state, meaning that the relationship between its pressure and its density differs radically from that of familiar substances. In many gravastar constructions, the pressure within the shell is dominated by tangential stresses forces that act along the surface rather than radially. These stresses can grow extremely large without causing the shell to collapse inward, allowing it to balance the repulsive interior vacuum energy while maintaining a stable radius. A typical gravastar in such models might have a mass comparable to several suns confined within a sphere only a few tens of kilometers across. The shell itself, however, would occupy only a minuscule fraction of that radius. Its thickness could be smaller than the size of an atomic nucleus, so that in a cross-section the shell would appear as a nearly sharp boundary between the interior and exterior regions. Despite this, the shell carries a substantial share of the total mass and almost all of the structural integrity of the object. Its stiffness means that even a tiny fractional stretching of its circumference would require an enormous amount of energy, comparable in some estimates to the energy released by a supernova explosion. This property is sometimes used as an intuitive measure of how tightly bound the shell is. If some external process attempted to deform it, the response would be extremely resistant, redirecting the disturbance into vibrations and oscillations rather than permanent changes of shape. The thermal properties of the shell add another layer of strangeness. In order to avoid rapid emission of radiation that would drain the interior energy and destabilize the structure, the shell must be extremely cold when measured from the outside. Some models place its effective temperature only a tiny fraction of a degree above absolute zero. At such temperatures, ordinary matter would behave in unusual ways, with quantum effects becoming important on macroscopic scales. The shell material is therefore often associated with quantum condensate states or with other exotic phases that can exist in principle at low temperatures and high densities. These states allow particles to move in highly correlated ways, reducing random thermal motion and suppressing radiation. From the viewpoint of an external observer using infrared or microwave telescopes, a gravastar would be almost perfectly dark, radiating less than the cosmic microwave background that fills intergalactic space. Only the behavior of nearby matter and light, guided by the gravity of the object, would reveal its presence. Constructing such a shell consistently requires careful matching between the interior and exterior solutions of the gravitational field equations. Mathematically, this is done by imposing junction conditions at the shell radius. These conditions relate the jumps in curvature across the shell to the energy and pressure content of the shell itself. For most familiar materials, these conditions would not permit an extremely thin, highly stressed layer without tearing space-time or leading to rapid instability. For specific choices of the interior vacuum energy and the shell equation of state, however, the junction conditions admit stable configurations. In these, the shell radius remains fixed or oscillates slightly around an equilibrium size, and small perturbations damp away rather than grow without bound. The stability analysis is subtle because the same strong gravity that holds the shell together also magnifies any disturbances. Nevertheless, studies using simplified models suggest that gravastar shells can, under the right circumstances, persist for times much longer than the current age of the universe. The composition of the shell is one of the most uncertain aspects of gravastar theory. No known particle physics model predicts a clear candidate for a material with exactly the required properties, although several speculative possibilities exist. Some researchers propose that the shell might consist of a form of matter related to superconducting phases where electric currents can flow without resistance, extended into the relativistic regime and adapted to curved spacetime. Others consider more general quantum fields that condense into thin layers under strong gravity, forming domain walls or phase boundaries with large surface tension. Surface tension is the energy cost per unit area of increasing the size of an interface. In the context of a gravastar, a very high surface tension would naturally resist changes in the shell area, supporting the idea that deforming the shell even slightly would require immense energy. What unites these ideas is the requirement that the shell behave like the most rigid material allowed by the laws of physics, while remaining so cold and so thin that it produces almost no radiation. From an astrophysical standpoint, the exact microphysics of the shell may not matter for many observable properties. The gravitational field outside depends only on the total mass and radius, not directly on the internal composition. As long as the shell is thin and located just outside the would-be horizon radius, the space-time geometry seen by orbiting stars accreting gas or passing light rays will mimic that of a black hole to a very high degree of accuracy. Only processes that probe the immediate vicinity of the surface, such as the behavior of infalling matter at extremely late stages or the details of gravitational wave emission during violent events, would reveal any difference. This separation between internal complexity and external simplicity mirrors in a different way the situation with black holes themselves. Classical black holes are described by only a few parameters despite potentially complicated formation histories. Gravastars, if they exist, would share this external simplicity, while encoding a more elaborate structure in their shells and interiors. Although the shell sits at the boundary between two radically different regions, it is not merely a mathematical artifact. In the gravastar scenario, it is the physical entity that prevents the formation of an event horizon and a singularity. It holds back the interior vacuum energy from unrestrained expansion and keeps the exterior spacetime from collapsing further. The existence of such a material forged in the brief and violent moment when a massive star dies is therefore the central physical claim of the gravastar hypothesis. If nature can create and maintain this shell, then a new class of compact objects could populate the universe, lurking wherever conditions once favored the birth of what would otherwise have been black holes. In everyday experience, empty space seems to be a simple absence of matter and radiation. Air can be pumped out of a container, light can be blocked, and what remains appears to be nothing at all. Modern physics gives a different description. In the framework of quantum field theory, every type of particle is associated with a field that extends throughout space. These fields do not vanish completely, even when no real particles are present. Instead, they fluctuate around a lowest energy state, the quantum vacuum. The vacuum is not filled with ordinary particles moving around, but it does carry energy, and it can respond to external conditions such as boundaries, strong fields, or rapid expansion. This idea is abstract, but it has observable consequences. Small shifts in the energy of atomic levels and tiny forces between closely spaced metal plates can be explained by taking the quantum vacuum into account. These laboratory effects show that what is called empty space in everyday language behaves at the fundamental level like a medium with structure and energy. On cosmic scales, the vacuum also appears in observations. Measurements of the expansion of the universe over billions of years indicate that the rate of expansion is not slowing down under the pull of gravity from matter alone. Instead, distant supernovae and the distribution of galaxies suggest that a form of uniform energy permeates space and drives an accelerated expansion. In the simplest interpretation, this energy is associated with the quantum vacuum and is often described through a parameter in the equations of general relativity called the cosmological constant. The inferred vacuum energy density on these large scales is small when measured in everyday units, but because it fills all of space, it has a significant influence on the dynamics of the universe. It acts with a negative effective pressure, so that rather than pulling matter together, it works against gravity and causes the expansion to speed up. This behavior demonstrates that vacuum energy is not just an accounting detail in theoretical calculations. It can, in principle, shape the evolution of spacetime itself. Gravastar models make use of the same basic concept, but apply it in a very different regime. Instead of a gentle vacuum energy that acts over billions of light years, they consider an interior region where the vacuum energy density is extremely high, concentrated within a sphere only a few tens of kilometers across. In these models, the collapse of a massive star forces the quantum vacuum into a new configuration. The transition is sometimes described as a phase change, similar, in a loose sense, to the way water can change into ice or vapor when temperature and pressure cross certain thresholds. Here, the changing quantity is not the arrangement of molecules, but the state of the underlying fields in curved spacetime. Under extreme compression, the lowest energy configuration inside the collapsing core may switch from one with relatively low vacuum energy to one with a much higher value. Ordinary particles are no longer stable in that region and effectively dissolve into the new vacuum state. What remains is a central domain filled with high vacuum energy and negative pressure. The gravitational effect of this interior is repulsive in the sense used in general relativity. The negative pressure contributes to the source of the gravitational field and tends to push space-time outward. This does not mean that objects near the boundary feel a simple outward force. Gravity, near a compact mass, remains attractive for matter outside the shell. Instead, the repulsive effect appears in how the interior region resists further compression and tries to increase its volume. The shell that surrounds it must counter this tendency. The balance between the interior vacuum and the shell defines a stable radius where inward and outward influences cancel. If the vacuum energy density inside were slightly higher, the shell would be pushed outward until its increased area and the changed curvature adjusted the balance. If the density were slightly lower, gravity would compress the shell inward. In a stable Gravastar configuration, these opposing responses are tuned so that small deviations do not grow. Mathematically, the space-time inside such an object resembles a simple solution of the gravitational field equations known for describing a universe dominated by vacuum energy. Distances in that region grow with time if left unconstrained, and light rays follow paths characteristic of an expanding space. However, in a Gravastar, the interior is bounded by the shell which fixes a finite volume. Light emitted inside may never reach the shell in a straightforward way, because the geometry can effectively trap it, and any local tendency toward expansion is held in check by the boundary conditions. From the outside, The metric approaches the form associated with a compact mass of a given size. The behavior of test particles, light rays, and orbiting bodies is therefore nearly identical to that predicted for a black hole of the same mass. Only extremely precise measurements in the immediate vicinity of the surface or during rapid dynamical changes would reveal the subtle differences due to the presence of an interior vacuum region instead of a true event horizon. The notion that vacuum energy can change value depending on conditions is not unique to gravastar theory. In many models of fundamental physics, the vacuum is not a single immutable state, but one of several possible phases. Early universe cosmology often invokes transitions between high-energy and low-energy vacuum states to explain periods of rapid expansion and the generation of structures from quantum fluctuations. In particle physics fields, such as the Higgs field, acquire non-zero values in the vacuum, giving mass to elementary particles through their interactions. These examples suggest that the properties of the vacuum are not fixed once and for all, but can depend on the configuration of fields and on the history of the system. Gravastars extend this line of thought to the environment of a collapsing star. They propose that under sufficient compression, the vacuum inside can undergo a transition to a high-energy phase that is locally stable once established. This view of vacuum energy changes the way the interior of a compact object is described. Instead of a point of infinite density at the center, there is a finite region where the energy content is smoothly distributed and the curvature remains large but bounded. The shell marks the location where the interior vacuum state meets the external region, which is mostly empty, except for any surrounding matter or radiation. Conceptually, the gravastar replaces a singularity and an event horizon with a configuration in which everything remains at least in principle describable by the same laws of physics used elsewhere without requiring infinities or a breakdown of predictability. In practice, however, the physics of vacuum transitions under strong gravity is not yet understood in detail. Theoretical models rely on simplified assumptions about the fields involved and on symmetries that may not hold exactly in nature. Different choices lead to different possible interior structures, and it is not yet known which, if any, correspond to real astrophysical objects. Despite these uncertainties, the idea that what appears as empty space can store and release vast amounts of energy is firmly embedded in both theory and observation. Gravastars represent an attempt to apply this idea to the end stages of stellar evolution. They take the known presence of vacuum energy on cosmological scales and ask whether an extreme local concentration of similar energy could form during collapse, stabilized by a surrounding shell of exotic matter. The question is not only whether this configuration is mathematically allowed, but also whether the processes in dying stars naturally steer toward it, rather than toward classical black holes. Answering this requires a better understanding of how quantum fields behave in highly curved spacetime and more detailed comparisons between the predictions of gravastar models and the growing body of data on compact objects in the universe. In modern physics, the idea that space is filled with fields is not only a mathematical convenience, but a central part of how particles and forces are described. Every type of particle corresponds to a field that extends everywhere, even in regions where no actual particle is present. The quiet state of these fields, their lowest energy configuration, is what is called the quantum vacuum. In this state, no definite particles move through space, yet fluctuations remain. These fluctuations can briefly create and destroy particle pairs, shift energy levels, and respond to boundaries. Although these processes cannot be seen directly with the naked eye, they leave measurable signatures that have been tested in laboratories. Tiny forces between closely spaced metal surfaces, small corrections to atomic spectra, and other subtle effects all point to the same conclusion. What is commonly called empty space behaves under careful measurement as a structured background with energy and with the ability to influence physical processes. In ordinary environments, the energy associated with the quantum vacuum is modest when measured over human scales. Between air molecules in a room or between atoms in a solid, the vacuum contributes only small corrections. On the scale of the universe, however, even a small vacuum energy density can matter. Observations of distant galaxies and supernovae show that the expansion of the universe is speeding up rather than slowing down. This accelerated expansion is most simply explained if space is filled with a form of energy that does not dilute in the same way as ordinary matter when the universe expands. A constant vacuum energy density fits this role. Its presence in the equations of general relativity produces a repulsive effect on cosmic scales, counteracting gravity from matter and driving the overall expansion to accelerate. This interpretation connects the behavior of the largest structures in the universe with properties of the smallest scales, where quantum fields define the vacuum state. Gravastar models rely on the same ingredients, but apply them in a much more concentrated way. Instead of a gentle vacuum energy spread through all of space, they consider a region deep inside a collapsed star, where the vacuum energy density has become extremely high. Ordinary matter no longer remains in familiar forms there. The pressure and density required to support the collapsing core surpass those that known particles and interactions can sustain. In some theoretical treatments, when this regime is reached, the vacuum state itself changes. The fields that define the vacuum settle into a different configuration with a higher energy density and a strong negative pressure. Practically, this means that the very thing that is usually treated as the baseline of empty space becomes the main contributor to the mass and internal pressure of the object. The interior volume is then described not as a collection of particles, but as a domain filled by this high-energy vacuum. The energy density in such a domain, when translated into mass through the relation between mass and energy, can be enormous, comparable to what would be found inside a black hole of similar mass yet distributed smoothly, rather than concentrated at a single point. A useful way to understand the difference is to consider how much of any given region is already vacuum, even in everyday conditions. Atoms consist mostly of empty space with a small nucleus, and electrons occupying orbitals that extend over relatively large distances. Solids and liquids consist of atoms arranged in patterns, but even they are largely empty when considered at the scale of their internal structure. The vacuum is present between atomic nuclei, between atoms, and between molecules. In this sense, most of the volume in any piece of matter is already vacuum. In usual circumstances, this vacuum remains in its low energy state and acts as a passive background. In the Gravastar context, the idea is that the collapse of a star brings so much mass into such a small region that the vacuum in that region can no longer stay in the same state. It is forced into a high-energy configuration, and because vacuum energy gravitates this new configuration, strongly influences the space-time inside the object. The notion that the vacuum can exist in different states is familiar in high-energy physics and cosmology, where transitions between vacua are used to model events in the early universe. During these transitions, regions of space can shift from a high-energy vacuum to a lower one, releasing energy in the process. Gravastar scenarios explore the opposite direction on a local scale in which the vacuum inside a collapsing star moves from a lower energy state to a higher one under compression. This is not yet supported by specific experimental evidence, but it is permitted by some theoretical frameworks that allow multiple possible vacuum states. In those frameworks, the local state of the vacuum depends on the balance of fields and on the conditions imposed by gravity. The presence of an extremely strong gravitational field in high densities can tilt this balance and make an otherwise disfavored vacuum configuration locally stable. Once such a high-energy vacuum region forms, its properties are simple in one important sense. The energy density and pressure are uniform throughout the interior, and the equations of general relativity admit a compact description of the resulting space-time. This simplicity is useful because it allows fairly direct calculations of how such an interior would curve space-time and how it would match to the exterior solution outside the shell. It also emphasizes a contrast with more complicated models of collapsed cores that rely on layers of different types of matter. A gravastar interior is not built from successive shells of nucleons, hyperons, quark matter, or other exotic particles. Instead, it is treated as a single domain, where the vacuum itself carries the load. The complexity is shifted to the question of how this domain forms and how it is stabilized by the shell. From an observational perspective, the detailed microphysics of the interior vacuum is largely hidden. Photons and particles from the outside cannot enter and return with information because the shell and the intense gravitational field near the surface keep them from probing deep inside. Gravitational waves generated by the motion of the object as a whole can carry information about its overall structure, but they are sensitive mainly to the mass distribution at large scales, not to the fine details of the vacuum state. As a result, a gravastar and a black hole of the same mass and radius can appear almost indistinguishable to many types of measurement. They bend light in the same way influence the orbits of nearby stars similarly, and shape accretion flows into comparable patterns. The difference between them lies in what they assume about the part of the universe that is hardest to access experimentally, the behavior of the vacuum at extremely high densities and curvatures. This focus on the vacuum turns gravastar research into a meeting point between astrophysics and fundamental theory. Astronomical observations constrain the mass, size, and external gravitational field of compact objects. Theories of quantum fields in curved spacetime and attempts to unify gravity with quantum mechanics suggest possible behaviors for the vacuum under extreme conditions. Gravastar models use the observational facts as boundary conditions and explore whether plausible vacuum behavior can fill the interior without introducing singularities. If such models can be made consistent with all known data, they offer one possible answer to the question of what happens when a massive star dies. They do not change the observed external story of bright supernova explosions and dark compact remnants. Instead, they propose a different internal script in which the most important actor is not dense matter, but a phase of the vacuum that only appears when gravity compresses space to its limits. In a gravastar, the combination of a high-energy vacuum interior and an ultra-rigid shell creates what can be described in technical terms as a static or quasi-static configuration. The interior tends to expand because the negative pressure associated with the vacuum energy favors an increase in volume. The exterior space-time dominated by the gravitational field of the total mass tends to draw matter inward. The shell sits at the interface, and its structure reflects this balance. On one side, it feels the outward push of the interior vacuum. On the other side, it experiences the inward pull of gravity from itself and from any remaining matter outside. In equilibrium, these influences cancel, and the shell remains at a fixed radius. This does not mean that the object is perfectly motionless inside. Quantum fields may still fluctuate, and the shell can support small oscillations, but these motions occur around a stable average state rather than leading to runaway collapse or expansion. The language of effective potential is often used to describe such a situation. For small radial displacements of the shell inward or outward, one can calculate how the total energy of the system changes. If the energy increases when the shell moves away from its equilibrium position, then the configuration is stable. The shell behaves like a mass attached to a spring in a simple model oscillating around a minimum of the effective potential. In detailed gravastar analyses, this effective potential depends on the interior vacuum energy density, the shell equation of state, and the total mass. For some choices of these parameters, the potential has a clear minimum indicating stability against small perturbations. For other choices, no stable minimum exists, and the system would either collapse further or disperse. The existence of a region in parameter space where stable gravastars can form is therefore a theoretical statement that such objects are not forbidden outright by the underlying equations. It does not guarantee that nature actually produces them, but it keeps the possibility open. The idea of the shell as a prison for the interior vacuum reflects the fact that in the absence of the shell, the high-energy interior would tend to expand and dilute much as the vacuum energy in cosmological models drives cosmic acceleration. However, the gravitational field of the total mass and the properties of the shell keep this tendency in check. The shell must be strong enough to resist the pressure, but also thin enough and located close enough to the would-be horizon that the external geometry remains nearly identical to that of a black hole. In most constructions, the radius of the shell differs only slightly from the radius that would define the event horizon for a black hole of the same mass. The difference can be tiny when measured in physical units. This proximity has important consequences. First, it means that time dilation at the shell is extreme. Processes on the shell that might take a short duration in local proper time can appear to stretch over long periods when measured by a distant observer. Second, it means that signals emitted from near the shell are highly redshifted as they climb out of the gravitational well. Their energy decreases, their wavelengths lengthen, and by the time they reach distant detectors, they can be so faint and stretched that they blend into background noise. These effects make the gravastar interior and shell effectively hidden from straightforward observation, even though no event horizon, in the strict sense, is present. From the standpoint of fundamental physics, the absence of a true event horizon and singularity matters. Information about matter that falls into a gravastar is not destroyed at a point of infinite density. Instead, it becomes encoded in the degrees of freedom of the shell and interior fields. The precise way this happens remains an open question, and many gravastar models do not spell out a detailed bookkeeping of information. Still, the framework allows in principle for information to be preserved because there is no region where the classical description breaks down entirely. The shell and interior are just extremely unusual but finite physical systems. Any radiation or matter that interacts with the gravastar can at least in concept influence the state of these systems. For an external observer, the effective behavior may still resemble information loss because, in practice, it is impossible to recover detailed information from an object that is almost perfectly dark and that evolves only extremely slowly. Yet, in a full theoretical description that combines gravity and quantum mechanics, the distinction between actual destruction of information and practical inaccessibility is important. Gravastars are motivated partly by the desire to avoid true information destruction. The balance that holds the gravastar together also raises questions about how such an object would respond to changes in its environment. If additional matter falls toward the gravastar, the shell must adjust. Some of the infalling matter will be converted into additional energy in the shell or interior, increasing the mass, and perhaps slightly changing the radius. The stability condition requires that the effective potential adjust so that a new minimum forms. In model calculations, one can track how the equilibrium radius depends on the total mass. Generally, more massive gravastars are larger in radius, but the radius grows more slowly than the mass. This means that as mass is added, the surface approaches the condition where a horizon would form if the shell did not provide support. The shell continues to hold the configuration just outside this threshold. Conversely, if the gravastar were somehow to lose mass, perhaps by emitting radiation or ejecting part of the shell, the equilibrium radius would decrease. The system could move through a series of quasi-static states as it gains or loses mass, always maintaining the balance between interior and exterior influences, as long as the parameters remain within the stable region. Over very long time scales, quantum processes might allow the gravastar to slowly radiate energy somewhat analogous to the way black holes are predicted to emit radiation through quantum effects near the horizon. The details would be different because the presence of a physical shell changes the boundary conditions. In some scenarios, the radiation could be dominated by modes associated with oscillations of the shell or with excitations of fields in the interior. At present, such processes are speculative and not yet described by a complete theory. What is clear is that if gravastars exist, they would be extremely long-lived. Their internal timescales set by the high densities and strong gravity are short, but when translated through gravitational time dilation to an external frame, their evolution might appear almost frozen. The image that emerges is of an object that has achieved a kind of dynamical stalemate, where expansion and collapse are held in near-perfect counterbalance. In that stalemate, superdense nothing, in the form of high-energy vacuum, remains trapped for periods that can exceed cosmic ages, confined not by walls of ordinary matter, but by a shell and gravitational field operating at the limits allowed by known physics. From far away, the Gravastar simply adds its mass to the gravitational landscape of the universe, shaping orbits and bending light like any compact object. Only by examining the precise conditions near its surface, or by probing its response to extreme disturbances, could an observer hope to tell that beneath its almost featureless exterior, a delicate balance maintains a prison for superdense nothing at its core. From a distance, gravastars are designed by their own equations to be almost indistinguishable from black holes. The gravitational field outside any spherically symmetric object depends in a simple way on its total mass and on how that mass is distributed with respect to radius. As long as the mass of a gravastar is confined inside a region very close to the radius that would mark the event horizon of a black hole, with the same mass, the geometry of space-time outside that radius matches the black hole solution with very high precision. Test particles following orbit's gas, spiraling inward under gravity, and light moving past the object all respond primarily to the overall curvature, not to the detailed internal structure. This means that many of the signatures long used to infer the presence of black holes can also be produced by gravastars. Astronomers have found compact objects with masses a few times that of the Sun in binary systems, where a normal star orbits an unseen companion and transfers gas to it. The gas forms an accretion disk, heating up as it falls deeper into the gravitational potential and radiating strongly in X-rays. The pattern of variability in this radiation, the inferred size of the emitting region, and the orbital dynamics all point to a very compact, massive object. In standard interpretations, these are stellar mass black holes. A gravastar with the same mass and radius, however, would generate almost identical observational features. The gravitational field that controls the disk is the same, and the innermost stable circular orbit, which sets a characteristic inner edge for the flow, lies at nearly the same location. As gas crosses this orbit and continues inward, general relativity predicts that it will plunge rapidly toward whatever occupies the central region, converting gravitational energy into radiation. In the case of a black hole, this radiation comes from the gas as it heats and shears before it passes through the event horizon and disappears from view. For a gravastar, the gas would instead approach the physical shell. In principle, matter striking a solid surface could produce a distinct observational signature because the energy of impact would be released at or near the surface rather than carried across a horizon. The radiation could be thermal as the surface absorbs and re-radiates energy, or it could emerge in bursts as accreted matter is processed. The crucial point is that the shell radius lies so close to the would-be horizon that any emission from the surface is subject to extreme gravitational redshift and time dilation. Photons climbing out of the deep gravitational well lose energy and are stretched to longer wavelengths, and processes occurring on the shell are seen by distant observers as slowed. Model calculations show that under realistic accretion rates, the extra light produced by a surface can be heavily suppressed and spread out over long time scales, making it difficult to distinguish from the emission generated in the accretion flow itself. In practice, current observations of X-ray binaries and other compact sources do not yet rule out such subtle surface effects. Supermassive compact objects in galactic centers present a similar situation. The motions of stars near the center of the Milky Way, tracked by large telescopes with high-resolution imaging, indicate a dark mass of several million suns contained within a region smaller than the orbit of Mercury. The standard picture identifies this mass with a supermassive black hole. A gravastar with the same mass and a radius only slightly larger than the corresponding horizon radius would generate the same gravitational field guiding stellar orbits in the same way. The appearance of the central region at radio wavelengths imaged by networks of telescopes that combine their signals to achieve very fine angular resolution shows a dark patch surrounded by a ring of emission from gas. The size and shape of this shadow match expectations for a black hole, but they also match the prediction for a gravastar whose surface lies extremely close to the horizon radius. Light rays passing near the object follow paths determined by the space-time curvature outside, forming a ring of bright emission and a central dark area where photons are captured or strongly deflected. As long as the surface emits little radiation, either because it is extremely cold or because any emission is strongly red-shifted, the observable image remains dominated by the properties of the accretion flow just outside. This is why the current imaging data are consistent with both interpretations. The time behavior of infalling matter offers another place where differences might appear. For a black hole matter that falls through the event horizon does so in a finite proper time according to its own clock, but appears to freeze near the horizon from the perspective of a distant observer, its signals becoming more and more red-shifted and delayed. For a gravastar, there is no true horizon. Infalling matter can reach the shell, interact with it, and potentially modify its state. However, because the shell sits at a radius where gravitational time dilation is already extreme, the outside observer still sees the approach and interaction as a very slow process. In idealized models, the time required for observable signatures of the surface to become apparent can exceed the current age of the universe. This means that even if gravastars have surfaces with distinctive physics, those features may be practically invisible on human or even astronomical timescales. Gravitational lensing, the bending of light around massive objects, provides further constraints. Measurements of lensed background sources such as stars near galactic centers or bright distant quasars depend on the mass distribution and on how close light rays pass to the compact object. Because the external metric of a gravastar is so similar to that of a black hole at all radii accessible to these rays, the lensing patterns are almost identical. Certain very precise observables, such as the detailed structure of photon rings formed by light that orbits the object several times before escaping, might eventually reveal small deviations. These would arise from the slight difference between having a horizon and having a reflecting or absorbing surface. Photons that reach the surface could be absorbed or scattered, altering the balance of trajectories that contribute to the image. The differences, however, are subtle and demand angular resolution and sensitivity beyond what is currently available. Another potential discriminator lies in the quasi-periodic oscillations and other timing features seen in the light curves of some accreting sources. These features are thought to arise from motion in the inner regions of the disk, where general relativistic effects shape the dynamics. If the inner boundary condition is set by a horizon matter, and patterns can disappear into it. If the inner boundary is a surface, waves and structures in the disk can reflect and interact differently. Detailed numerical simulations show that these differences could, in principle, affect the frequencies and amplitudes of observed timing signals. At present, the uncertainties in modeling complex magnetized turbulence and radiation processes are large enough that clear conclusions are hard to draw. The same timing features that might reveal subtle differences also depend sensitively on unknown properties of the disk and magnetic field. As a result, both black hole and gravastar interpretations remain compatible with the broad range of observed behaviors. In all these cases, the gravastar functions as a near-perfect imitation of a black hole. The external gravitational field is the same to a high degree of accuracy, and the ways in which matter and light move in that field reproduce the familiar signatures. The main differences appear only in regimes that are challenging to probe extremely close to the surface over very long timescales, or in response to rapid, strong disturbances. This close mimicry is part of what makes the gravastar proposal both difficult to test and scientifically interesting. If nature does realize such objects, then much of the evidence currently interpreted as proof of black holes would remain valid as evidence for very compact, dark masses. But the internal story would change. The universe would contain not only regions where space-time curves into a singular point hidden behind a horizon, but also regions where high-energy vacuum and exotic matter form stable structures at the threshold of collapse. Deciding between these possibilities requires methods that do more than map the static gravitational field. They must listen to how these objects respond when they are disturbed and examine the fine structure of the signals that carry information from their most extreme environments. Black holes occupy a special position in theoretical physics because they sit at the intersection of general relativity and quantum mechanics. General relativity describes gravity as the curvature of space-time caused by mass and energy. Within that framework, a sufficiently massive and compact object inevitably produces an event horizon, and continued collapse leads to a singularity where curvature becomes infinite and the classical description breaks down. Quantum mechanics, in contrast, is built on linear evolution of states and strict conservation of information. When these two frameworks are combined in a simple way, tension appears. A classical black hole with an event horizon hides whatever falls in. When quantum effects near the horizon are taken into account, calculations indicate that black holes emit radiation with a thermal spectrum. This radiation carries energy away and can, over very long timescales, cause the black hole to lose mass and eventually evaporate. The combined picture suggests that matter and radiation carrying detailed information about their microscopic state fall into a black hole. The hole emits almost featureless thermal radiation, and after complete evaporation, only this radiation remains. The initial detailed information appears to be lost in conflict with the usual quantum mechanical principle that information is preserved in time. This is the black hole information problem. Many proposed resolutions exist, ranging from modifications of quantum mechanics to new structures at or near the horizon, but no consensus has been reached. Gravastars address this tension by altering the internal structure of the compact object. In a gravastar model, there is no singularity and no true horizon. Instead, there is a finite radius shell surrounding a high-energy vacuum interior. The gravitational field outside looks for almost all practical purposes like that of a black hole with an event horizon just inside the shell. However, since there is no region where space-time curvature diverges and no boundary that fundamentally prevents information from influencing the outside, the theoretical possibility exists for information to be preserved. Matter and radiation falling toward the gravastar do not pass through a horizon and vanish into a singularity. They encounter the shell and the interior fields. In principle, their influence on these degrees of freedom can be encoded in the microscopic state of the gravastar. Any radiation that eventually leaks out, whether through slow quantum processes or through dynamical events, could carry correlations that preserve information, even if such correlations are practically impossible to detect. Gravastar models therefore offer an example of how the global rules of quantum theory might remain intact while the macroscopic appearance of a dark compact object is maintained. The removal of the singularity is another motivation. Singularities are not places where physical quantities are simply very large. They are points where the equations as currently written cease to make sense. Most physicists interpret their appearance as a sign that the theory is incomplete in that regime. In many scenarios, one expects that a more complete description, perhaps involving quantum gravity, will smooth out the singularity and replace it with a region where quantities remain finite. Gravastars implement such a replacement at the level of classical general relativity, coupled to fields with suitable properties. The interior high-energy vacuum region has large but finite curvature and energy density. The shell marks a well-defined surface where interior and exterior solutions match. The entire configuration remains within the domain of the equations without requiring an undefined central point. This does not mean that gravastars are the only or correct way to avoid singularities, but they demonstrate that alternative end states exist within broadly familiar physics. At the same time, gravastars introduce difficulties of their own. The exotic matter required for the shell has no clear realization in current particle physics. The conditions under which the vacuum would transition to the high-energy interior phase inside a collapsing star are not derived from a complete theory, but are imposed as plausible possibilities. The equations are often treated in an idealized spherically symmetric form, whereas real astrophysical collapse can involve rotation, magnetic fields, and asymmetric motions. Extending gravastar models to include these realistic features is challenging. Rotating versions of gravastars have been studied in simplified forms in which the shell and interior are allowed to spin. These models show that rotation can be accommodated and that the external geometry still mimics that of a rotating black hole closely, but they also reveal new modes of instability. The shell may develop non-spherical perturbations, and the behavior of such perturbations under strong gravity is complex. Whether rotation tends to destroy gravastars or simply changes their observable properties remains an open question. There are also issues related to formation. The standard black hole picture arises naturally in numerical simulations of core collapse and compact object mergers in general relativity, when matter is treated with realistic equations of state. Horizons form when matter is compressed inside the critical radius, and the simulations evolve toward black hole solutions. To obtain a gravastar instead, additional physics must intervene before the horizon forms. Some studies introduce effective terms representing vacuum transitions or exotic pressures to see whether they can halt the collapse and generate a shell. Under certain tuned conditions, the collapse can bounce and leave behind a compact configuration without a horizon. The viability of this mechanism under natural conditions with noise asymmetries and realistic microphysics is still uncertain. Gravastars therefore move the mystery rather than eliminating it. They replace the question of how to resolve singularities and information loss with questions about how exotic shell matter and vacuum transitions behave. Nonetheless, this shift can be useful. It frames the problem in terms of concrete properties of fields and materials which might be studied with theoretical tools or interpreted within future unified theories. It also suggests observational strategies that differ from those focused solely on static properties. If gravastars and black holes are almost identical when undisturbed attention must turn to how they respond to changes. This leads naturally to the study of dynamic events involving compact objects such as mergers and accretion outbursts, and to the analysis of the waves and radiation they emit. Within that broader program, gravastars serve as one possible class of alternatives against which observational data can be compared. If data systematically agree with black hole predictions and disagree with gravastar predictions, then gravastars can be constrained or ruled out. If, on the other hand, subtle discrepancies appear that match the behavior expected from objects with shells and high-energy interiors, then the case for gravastars or related structures becomes stronger. In this way, theoretical work on information singularities and compact object interiors is linked directly to measurements of signals from some of the most energetic events in the universe. The emergence of gravitational wave astronomy has opened a new way to study compact objects like black holes and any possible alternatives. Gravitational waves are ripples in space-time produced when massive bodies accelerate, especially in asymmetric and rapidly changing systems. General relativity predicts that when two compact objects spiral toward one another and merge, they radiate energy in the form of these waves. Ground-based detectors, long laser interferometers with arms several kilometers in length, are designed to measure the minute stretching and squeezing of space as waves pass through the Earth. Over recent years, these instruments have recorded multiple events interpreted as mergers of stellar mass black holes and neutron stars. Each detection carries information about the masses, spins, and orbital dynamics of the merging objects encoded in the changing frequency and amplitude of the signal. The waveform from a compact binary coalescence can be divided into three phases. In the inspiral, the two bodies orbit one another at increasing speed as they lose orbital energy to gravitational radiation. The frequency of the waves rises in a characteristic way that depends on the masses and spins. In the merger, the objects collide and form a single, highly disturbed remnant. In the ringdown, this remnant settles into a more stable state, emitting waves with frequencies determined by its mass spin and internal structure. For classical black holes described by general relativity, the ringdown phase is dominated by a set of damped oscillations known as quasi-normal modes. Their frequencies and damping times are fixed by the mass and spin alone. This leads to the expectation that the late-time gravitational wave signal from a black hole merger should resemble a short burst followed by a rapid decay, like a single strike on a drum that quickly fades. Gravastar models predict a similar pattern for much of the waveform because the external gravitational field is almost the same during the inspiral and early merger. The two objects spiral together, and merge under the influence of the same curved space-time geometry. Differences emerge at the stage where the structure of the remnant near its would-be horizon becomes important. Instead of an event horizon, a gravastar has a shell and interior. When the merger remnant is a gravastar, the ringdown can be more complicated. Disturbances in the space-time and in the shell can reflect and reprocess gravitational waves. Some theoretical studies suggest that part of the wave train that would fall through a horizon in a black hole case can instead scatter between the effective potential barrier outside and the shell inside, leaking out in a series of weakened pulses. In the time domain, this appears as small delayed features superimposed on the main decay, sometimes referred to as echoes. In the frequency domain, these echoes can introduce fine structure in the spectrum of the ringdown. The detailed pattern depends on the exact position and properties of the shell and on how strongly it reflects or absorbs gravitational waves. The possibility of echoes provides a way in principle to distinguish gravastars from black holes. If detectors can measure the ringdown with sufficient sensitivity and resolution, analysts can search for deviations from the simple quasi-normal mode pattern predicted for black holes. The methods involve matched filtering, where theoretical templates are compared with the data to find the best match, and more general time-frequency analyses that look for excess power at specific delays. Early gravitational wave detections provided first tests of this idea. The data from those events are noisy and limited in duration, and the signals are relatively faint in the ringdown portion. When different groups analyzed the same events, some reported hints of late-time features that could be interpreted as echoes, while others found that the data were consistent with pure black hole ringdowns once uncertainties and noise fluctuations were taken into account. The differences often came down to choices in how to model the background noise and what statistical thresholds to apply. As more events were recorded, the combined data sets allowed stronger tests. Overall, no convincing, widely accepted evidence of echoes has yet emerged. The observed waveforms match the black hole predictions within the sensitivity limits of current detectors. At the same time, the limits on possible echo amplitudes are still compatible with many gravastar models, especially those in which the shell lies extremely close to the horizon radius and reflects only a small fraction of incident waves. In such cases, echoes would be weak and difficult to detect sitting near or below the level of instrumental and environmental noise. The search for echoes continues because each improvement in detector sensitivity data analysis techniques and the number of observed events increases the chances of spotting subtle deviations. Future ground-based facilities with longer arms and reduced noise, as well as planned space-based detectors that will listen for lower frequency waves from more massive mergers, are expected to provide clearer views of the ringdown phase. In anticipation, theorists are refining models of how compact objects with surfaces or other non-standard structures would respond to mergers. These models extend beyond gravastars to include other proposals, but the overall strategy is similar. First, compute the expected gravitational wave signal for a range of alternative compact objects. Then, define quantitative measures that capture the differences between those signals and the black hole baseline. Finally, apply those measures to the data to see whether any observed events favor one class over another. Another line of investigation focuses on how the presence of a shell affects the stability and oscillation modes of the remnant. The shell can support its own spectrum of vibrations coupled to the surrounding spacetime. After a merger, the combined object may ring in many modes at once, some dominated by the exterior geometry, others by the shell. The coupling between them can transfer energy back and forth and modulate the emitted waves. The frequencies of these modes depend on the shell properties, providing a possible diagnostic. Extracting such detailed information from real data is challenging because detectors measure only a single combined strain signal from the whole sky, and the sources are distant. Nonetheless, the mathematics of perturbations in curved spacetime offers a clear framework for what to look for. In this sense, Gravastar studies act as a laboratory for understanding how extra structure near the horizon scale would reveal itself in gravitational waves. Beyond individual events, statistical studies across many detections can look for systematic patterns. If all observed mergers are consistent with the black hole waveform family, and if the data quality is high enough to exclude significant deviations, then the parameter space in which gravastars or similar objects can hide shrinks. Conversely, if one event or a subset shows a consistent, reproducible departure that would signal the need to revisit the assumption that all compact merger remnants are black holes. At present, the situation remains open. Gravitational wave astronomy is still young. The first direct detection occurred only in the recent past on cosmic time scales, and the catalog of events, while steadily growing, is modest compared with the vast population of compact objects in the universe. Detectors are being upgraded, analysis techniques are becoming more sophisticated, and future instruments are planned that will broaden the accessible frequency range. As this observational network develops the ability to listen for the fine details of ringdowns and possible echoes, will improve. Gravastars in this context serve as one of several benchmarks. They offer a concrete alternative model whose predictions can be compared with data. Even if no evidence for them is found, the effort to distinguish them from black holes sharpens the tools of gravitational wave analysis and deepens the understanding of how the most compact objects in nature behave when pushed to their limits. For now, the waves recorded from distant mergers support the black hole interpretation, yet the precision is not sufficient to exclude all alternatives. The universe continues to broadcast signals from these extreme events, and each new detection adds a small piece to the puzzle of what truly lies inside the dark compact remnants that form when massive stars and compact binaries reach the end of their evolution. In the current picture of the cosmos, black holes occupy a central role as the final state of massive stars, as engines of active galactic nuclei, and as key sources of gravitational waves. Gravastars enter this picture as a speculative but mathematically consistent alternative, replacing the interior singularity and event horizon with a shell and a high-energy vacuum core. The external similarity between gravastars and black holes means that existing observations cannot easily separate the two possibilities. Instead, the distinction rests on the physics of regions that are almost but not quite hidden from view. As theoretical work and observations progress, several paths emerge by which this distinction might become more than an abstract argument. One path involves more detailed modeling of stellar collapse and compact object formation. Present simulations of massive star deaths and compact binary mergers already reproduce many observed features of supernova neutron stars and black hole candidates. These simulations are steadily being refined with improved treatments of neutrino transport, magnetic fields rotation, and nuclear microphysics. If in future models the inclusion of realistic quantum field effects in strong gravity regimes leads naturally to configurations resembling gravastars, then the idea of gravitational vacuum stars would gain support as a possible outcome of collapse. Conversely, if such effects can be shown to steer collapsing matter toward classical black holes under all plausible conditions, gravastars would become less likely. Another path runs through advances in fundamental physics. Efforts to unify general relativity with quantum theory, such as approaches based on quantum gravity string, inspired models or other frameworks, aim to describe space-time at the smallest scales. These theories often predict that singularities are resolved into finite structures and that the vacuum can have multiple phases. As these ideas mature, they may provide a more detailed account of what happens inside extreme compact objects. Some formulations might favor an interior like that of a gravastar with a high-energy vacuum region and a thin boundary, while others might predict entirely different structures. In this way, future developments in high-energy theory could either embed gravastars in a wider theoretical context or displace them with alternatives that better match the underlying principles. Observationally, the coming decades promise more precise measurements of compact objects across the electromagnetic and gravitational spectrum. Radio arrays with greater baselines and sensitivity could image the immediate surroundings of supermassive compact objects with finer resolution tracing not only the gross shadow, but also the detailed structure of photon rings and time-variable features in the emission. X-ray and gamma-ray observatories could map the inner regions of accretion flows with improved timing and spectral accuracy, searching for subtle deviations from patterns expected near classical horizons. Gravitational wave detectors on the ground are being upgraded, and new instruments are planned in space to listen to lower frequency waves from mergers of supermassive objects. Together, these facilities will provide a richer set of data on how compact objects behave in both quiet states and violent events. If all these observations continue to confirm the predictions of black hole models with increasing precision, the available space for gravastars will narrow. The shell would need to lie so close to the horizon radius and reflect gravitational and electromagnetic disturbances so weakly that it would become practically indistinguishable from a horizon in all measurable ways. Gravastars would remain mathematically possible, but physically irrelevant, a theoretical curiosity, rather than a description of real objects. If, however, careful analysis reveals consistent reproducible anomalies in timing, patterns, spectral lines, or gravitational wave ringdowns, then attention would turn to models that include surface effects or non-standard interiors. In that case, gravastars would stand among the candidates alongside other horizonless compact objects as potential explanations. The universe might then be found to host a more diverse population of dark remnants than currently assumed, with some behaving as classical black holes and others as vacuum-supported shells. The long-term evolution of such objects would also shape cosmic history. Black holes that slowly evaporate through quantum processes introduce a time scale on which even the most massive structures fade. Gravastars, if they radiate differently or more slowly, could persist for far longer, acting as lasting repositories of mass energy and information. In scenarios where vacuum energy plays an even more active role on large scales, compact vacuum-dominated objects might interact subtly with the cosmic expansion or with dark energy. These connections remain speculative, but they highlight how local questions about the fate of collapsing stars can link to global questions about the structure and future of the universe. For now, the concept of a gravastar serves as a reminder that familiar narratives in astrophysics may conceal underlying choices about how unknown physics is treated. The standard story of stellar death leads to black holes, partly because general relativity is extrapolated into regimes where it has not yet been fully tested and where quantum effects are likely to be important. Gravastars offer one way to modify that story without abandoning the tested parts of the theory. They keep the successful predictions of strong gravity while altering the behavior at the very edge of collapse. Whether nature takes advantage of this alternative remains an open question. It may be that every observed dark compact object is indeed a black hole as currently understood, and that any deviations from this picture are too small to matter. It may also be that some fraction of these objects are gravastars or related configurations hiding high-energy vacuum regions and exotic shells behind gravitational fields that look from far away entirely ordinary. As observations improve and theories evolve, the sharp line between these possibilities may blur into a spectrum of allowed behaviors. In that spectrum, the idea that nothing falls forever into a singular point, but instead encounters a complex boundary where space-time vacuum energy and matter interact in unexpected ways, remains one of the more intriguing options for how the universe organizes its most extreme structures. In any case, the study of gravastars encourages careful examination of assumptions that often remain hidden behind compact formulas and invites continued attention to the faint signals that might reveal a different interior beneath a familiar gravitational face.